One of the most important topics that we need to cover in this class is the topic of electrostatic interactions. As you'll see, this is something that will govern a lot of the behavior that we'll see in molecules and atoms throughout the course, and getting a firm understanding of how these things work is very important at an early stage. So matter, stuff we're made of. We already talked about some properties of matter. It has mass, it takes up space, but what holds it together? Is it gravity? When gravity holds planets together, is it the same for particles? Well, let's take a look. Our learning goals for this lesson are going to be to first define what is charge, then talk about charges on elementary particles, talk about the meaning of Coulomb's law, which governs the forces that are felt between electrically charged particles, and finally get an understanding, a qualitative understanding of how these charges work and how these electrostatic forces work. So we need to revise our properties of matter. It not only has mass and volume, but now also charge. Charge is an intrinsic quality of matter that usually can either be positive or negative, sometimes zero. So what is charge? Charge is basically the quality of matter that governs a force between particles. In other words, if it has charge, then it can experience this force, which we call an electrostatic force. It has units of coulombs, after a French physicist who studied electrically charged particles. A coulomb is actually quite large, as it turns out, much larger than the charge that we find on different elementary particles or atoms, but we'll deal with that in just a moment. So there are two varieties of charges. I already mentioned that there can be positive charges or negative charges. Now, is this important that there are positive and negative, and what if you get them wrong? What if you assign the wrong one to the wrong particle? Well, you may miss a point on a test, but the main point of this is that the assignment of these signs are arbitrary. Could be anything. In fact, we could use any pair of possibilities that are opposites, like black and white, or right and left, or up and down, good and bad, doesn't matter. What we're trying to indicate by this is that we have two fundamentally different kinds of particles, and if we call them positive and negative, it turns out there are some mathematical conveniences for that we'll take advantage of, but we could have called it anything. So what is the difference between a positive and a negative charge? Well, the real difference comes in this. When we look at the forces between particles, if two particles both have a positive charge or both have a negative charge, they will experience a repulsive force. They'll be pushed apart from one another. You may recall that that defines the force to be a positive quantity. If they have opposite signs, if one is negative and one is positive, then they have an attractive force. They're drawn together. The difference between these things are they establish a lot of what we know about matter and a lot of the qualities and properties of matter that are going to be most important to us in this course. Opposite charges attract, like charges repel. If you can remember that, you've got it down. So let's take a look at the elementary particles that are going to make up all matter. First, the electron has a charge of, and here I said it was a very small quantity, negative 1.602 yada 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 times 10 to the minus 19 coulombs. It's a very, very infinitesimal amount of coulombs that you find on an electron. What about a proton? Well, a proton has plus 1.602 yada 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 times 10 to the minus 19 coulombs, and a neutron has exactly zero. Now, it may seem like the electron and the proton have effectively zero, but the fact that they have something that's not zero is very important. You may notice that the two charges are alike in magnitude but opposite in sign. It turns out that this is the smallest possible charge that any piece of matter can have. So it only goes up from here. So that's the smallest you can have, and then you can have some multiples of that, and the rest is history. So how strong is the force between charges? Well, we call this the electrostatic force. And this fellow Coulomb, after whom the charge is named after, came up with a mathematical expression that describes what this force is like. And it looks like this. the force of electrostatic interaction is K times Q1, Q2 divided by R squared. So what are all these things in the equation? This is the only equation you're probably going to see in this course, so you can rejoice now that there are no further equations to look at, but I want you to understand what this one means. All right, these things that are in the top, these are the magnitudes of the charges. So there's the things that are written in terms of coulombs, like the proton and the electron. The R down there is the separation. It's the distance between those things. So in other words, the force between charged particles is going to depend upon the distance between them. And this K is just a physical constant. It doesn't do anything. It just simply converts the units of charge squared divided by distance squared and converts it into a force, a Newton of some kind. Now let's take a look at this equation and see what we can get out of it. The charges, the magnitude of the charges is in the numerator. This means that the larger they get, the larger the numerator gets, and the larger the force gets. All right, what about the distance between the charges? That's in the denominator. So that's Q1, Q2 divided by R squared. So the farther apart two charges are, the larger R will be, and the smaller the force will be. So in other words, the electrostatic force is going to be felt most intensely by particles that are close together and least by particles that are far apart. So when Q1 and Q2 have the same sign, what does that mean? Well, if they're, say, both greater than 0, then it's going to be a positive number in the numerator. Distance is always a positive number, and I can tell you that the physical constant there, K, is a positive number, so that means that the force is going to be positive, and we already associate that with a repulsive force. So we already have here a reminder that when you have two charges that have the same sign, this net a mathematical equation will give you a positive number, and force will be greater than 0. What if they have different signs? Well, now the product of the two charges will be less than 0. A positive times a negative always gives a negative. So that means that the force is less than 0, and we have an attractive force. So once again, this fits in nicely with assigning the charges to be positive and negative instead of white and black or whatever. Okay, by making them positive and negative, we can use this mathematically now to be consistent with our definition of force being attractive or repulsive between them. Now I want you to use this as a little bit of an exercise. So again, you may pause this video after I explain this. Here are 6 different setups, and I want you to look at this and decide which pair of charges represent the ones with the strongest attractive force. Okay, now pause the video and think this through a little bit. Did you get it? Well, as I've just shown you, 3 of these are repulsive because they have the same sign of the charge. So only 3 of these really need to be considered, and those are the other 3 with one blue and one red charge. All right, now all of these have the same charges. Basically, one is +1 and one is -1. How would you decide which one is the strongest charge? Well, we go back to the closer together they are, the stronger the force. So the strongest attractive force is going to be this one here in the middle. All right, and that's the one that is the answer to this question. You need to be able to look at these kinds of things and pick out which one is going to be the strongest attractive or strongest repulsive force. The one right below it would be the strongest repulsive force. Now, what if we have a more complicated system, and most molecules are more complicated? We have 3 charges now that are all interacting. You can think of there being 3 different pairwise interactions, a force between Q1 and Q2, a force between Q2 and Q3, and a force between Q1 and Q3. So what would be the force felt by these particles? Well, it's just the sum of these 3 forces. In other words, forces are additive. So even if we have a complicated system with lots of different forces in it, we're still going to have a relatively simple time of simply adding those forces together, and we can use that to determine the net effect of the system. So I have a few exercises for you to look at as part of this video, and it'll give you some practice in how to figure this out. So if we have the following set of forces, following set of particles, and let's assume they're stuck on that line. They can't move off the line. All right, they're all +1. What you want to do is to decide which direction the middle charge will move if we have a way of holding Q2 and Q3 in place. In other words, Q2 and Q3 are stuck where they are. Only Q1 can move. Which direction does it go? Okay, stop and think about that for a second and pause the video, and when you come back I'll talk about it a little more. Okay, now remember that the stronger force is felt by the particles that are closest together. And in this case, Q1 and Q2 are the ones closest together. So that's going to be the stronger negative force, stronger repulsive force. So the net effect is going to be, when you add those two forces together, that the Q1 charge is going to move to the right. It's going to try to get away from Q2. When it gets somewhere in the middle between these two charges, that's when the force will be equal on both sides and it probably won't move anymore. All right, here's another one. Which direction does the middle charge move in this case? Now in this case we have a negative charge in the middle and positive charges on the two sides, so we might infer that this is going to be attractive forces. But I want you to look carefully at the charges on either side and determine which direction this charge is going to move. So pause the video again and work it out. Okay, hopefully you've gotten the right answer. In this case, the magnitude of the charges is the deciding factor, and the charge on the right-hand side is a larger magnitude, so we should expect to see this particle move toward the larger charge. That is going to be the stronger attractive force. All right, so again, this particle moves to the right to resolve this situation. All right, now we've got the grand challenge. In this case, it's not the two end atoms or two end particles that are fixed, it is the two on the left. Those two are fixed in place, and what I want to determine is which direction will Q3 move. Will it move toward these atoms, or will it move away from them? Now, I'm going to give you a chance to think about this, and then I'll talk about it a little bit more. All right. As you look at this, you can see that there's an attractive force between Q1 and Q3, but there's a repulsive force between Q3 and Q2. Q2 is a little farther away, so in other words, we have some kind of balance of both an attractive force and a repulsive force. In this particular case, it turns out that because of this particular arrangement, Q3 moves toward those particles. All right, but it doesn't move toward it as strongly as it might if there was only Q1 there. Q2 does have the effect of pushing it a little bit away, so it weakens the force that it feels toward Q1. Now this is a situation that we're going to see somewhat in atoms and molecules, because if you think of Q1 as being like an electron, a negative charge, and Q2 and Q3 as being like protons, which are found in atomic nuclei, this is a situation where you might see two particles that are attracted toward one another, even though they have at the root a repulsive force. So the electron does, in a way, it screens the repulsive force that is coming from Q2 toward Q3. All right, I'm not going to make you do any complicated problems with this. What I want to give you is an intuitive feel for the possibilities that can come out of considering all these things. I'll give you the answer when it comes to what actually happens, and so hopefully you'll be well informed about that. But as long as you have a good feel for what's at the root of these problems, I think you'll get a lot greater meaning out of the things that we cover this semester. All right.